As our second example on conditional distributions and conditional expectations, let's go back to an example we saw earlier in this lecture, the rainfall distribution. So H is the annual rainfall, and it has a certain density function as you see on the screen. We first would like to find out what its mean and standard deviation are, and now let's put a conditional event. So let's define drought, and drought is defined in terms of H, that the random variable H is less than 1 meter. So with this conditioning event, we need to find out what is the mean and standard deviation of H in a drought year. So to do that, let's first find the unconditional mean as asked for, and the unconditional standard deviation. So if you just do the basic integration, if my calculations are correct, then the unconditional mean is about 1.4 meter, and the standard deviation is 0.3876 meter. Now let us bring in the conditioning event. So let A be the event that drought occurs, and it's defined as H is less than 1. So the conditional distribution function is P of, in the numerator we have P of capital H less than or equal to H and A divided by P of A. And now we bring in what is the event A itself, so that's H is less than or equal to 1. Because H is a continuous random variable, the probability of H less than 1 and H is less than or equal to 1 are the same. So if we now expand that, we get the distribution function defined in 3 ranges, as you see. It can't have negative values as before, so it's 0 there, but greater than 1, it also cannot have any values. So conditioned on the drought, the CDF attains the value of 1 at H equal to 1. Now if we differentiate this CDF, this conditional CDF, we get the conditional density. So the density of H given A is, we have non-zero values only in the range 0 to 1 and 0 elsewhere. Whether it's greater than 1 or less than 0, there is no density. And we need to make sure that this density still integrates to 1, so you can see that it does. So that's good. And now, as requested in part B, let us find out the conditional mean and the conditional standard deviation. So the first would be just to integrate the conditional density with respect to H, and the number comes to 0.75 meter, which is much less than the unconditional value of 1.44. If you now find the conditional expectation of H squared, you get 0.6, and if you subtract the mean squared from that, you get a standard deviation of 0.1936, which is also less than what it was at 0.38 in the unconditional case. So that would be another example looking at the effect of conditioning events on densities and expectations of random variables.